Hello, everyone. This is our project for BME 6055, Modern Biomedical Technologies, and our project is on the photocatalytic mask filter. And I'm Syed.
I am Manuel.
And I am Victor.
The reason we picked this topic for our project is due to COVID-19. Masks have become an everyday necessity now with the spread of COVID, and having a more efficient mask would make a significant difference in our spread of the disease. Our design filters and cleans the air and not just bypasses it. And these are the main components for our mask. We use a titanium dioxide HEPA filter, an ultraviolet LED with a 390 nanometer wavelength, and a 9-volt battery. And this is what our prototype looks like.
So our goal was to build basically a respirator filter. We thought about making a mask, but having electronics and making it so thick would make it pretty hard for it to be usable. So we decided to make something that would replace these respirator filters. So you can see on the top right, that's the top view. So it has a HEPA filter. Then in the middle, you can see on the bottom left, there's actually 2 layers of the titanium dioxide mesh. And then on the bottom, another HEPA filter. And then those are the 2 UV LEDs we use connected to a 9-volt battery. And when connecting LEDs to any battery, you have to make sure that they're rated at the correct voltage and current. If not, you can easily burn out these LEDs. So you have to take Kirchhoff's law into account that the drop over the whole system has to be equal to 0. So you just have to add a resistor in there to make sure that you don't burn out these LEDs.
So now I'm going to explain how the photocatalytic effect works. So our light source would hit our filter and it would cause the free radicals to form. These free radicals would interact with the pollutants, or in our case, any organic pollutants right over here. And redox reactions would occur, neutralizing the pollutant to where it's not going to be harmful. Ideally, the photocatalyst we would use is titanium dioxide. It's efficient in photoactivity, which means it creates free radicals very readily. It's very stable. It doesn't cost very much, and it's safer for the environment and for us. There are other photocatalysts that aren't as effective, but they're worth mentioning, which is zinc oxide, cadmium sulfide, and other sulfide semiconductors. So comparing our design versus others, our HEPA filters are better than N95 masks. Our rating is 99.7% effective at removing particles 0.3 microns. Any COVID-19, for example, is smaller than 0.3 microns, but our filters work better at filtering those smaller particles out, because particles smaller than 0.3 microns, they don't move in a linear motion. They follow Brownian movement, which means they just they move very sporadically because they hit air molecules or whatever other molecules that's in the environment, and it just bounces off of them, which makes them easier to get caught in the filter. And again, the UV, like I mentioned before, the UV light and the photocatalytic effect break down the carbon-based pollutants and they neutralize them essentially.
So as you mentioned, this is just a prototype right now. There are a few things we thought of that could improve the efficiency and make it better. And like we mentioned, TiO2 has a relatively high band gap. It is usable, but at 3.2 eV, the only light that'll work to create this photocatalytic effect will actually be UVA, which is the lowest wavelength UV light, but the most powerful. So that's why we had these UV LEDs. Obviously, the ones we used were not UVA. We used UVC just because of safety reasons. We didn't have the proper PPE to work with UVA at home, and then they're also a bit more expensive. But going off that, there are a few ways to modify the TiO2 mesh to lower its band gap. We read quite a few articles and publications where they use different techniques to lower this. Some of them are metal and non-metal doping, dye sensitization, surface modification, fabrication of composites, and there's a few more. But for example, with doping, what happens is you add another element into the TiO2 mesh to create a different surface characteristic where it can lower the band gap and lower all the energy necessary for this. For example, you can add metals like platinum or silver, and this can severely lower it. Or there's others like non-metals like nitrogen can be added, and they can also lower it from like 3.2 to the low 2s, which is a big difference. And if you lower it enough, you can reach just using regular light or regular LED, so you don't need these UV LEDs that could be dangerous. Obviously, with UVA, you also have the addition of the UVA itself, cleansing a bit of the pollutants, but by lowering it, the band gap, we would need a smaller battery, the lifespan would be longer, and it would be safer to use. And then on top of that, we also thought of a different way of making the filter itself. So right now it's one block, but if this would be mass manufactured, we think it would be the best to have like a modular design where each layer can be replaced by itself in case it breaks or in case you need replacing. So the HEPA filter should be replaced by themselves, and then the titanium dioxide layer should be replaced by itself. So it would be like a clip-on to itself. And then we also wanted initially to add an activated carbon layer to filter out smells. Since HEPA doesn't filter out smells, it just filters out pollutants, and then the titanium dioxide doesn't filter out smells that great either. The problem with activated carbon is that it's pretty heavy, and this is already a pretty big filter. Obviously, it would be a bit smaller than this in real life, but by adding activated carbon, it would just add too much weight on, and having too much weight in the front of the face isn't really comfortable, especially for long periods of time. So thank you. We will be taking questions in class.